In this video, we will learn the skills to build a custom machine for SURFCAM machine simulation option. To build a custom machine, first select any one of the sample files, then open the Operations Manager, right mouse button select on a setup section, edit setup information, go to machine definition, and based on the current toolpaths that are in the setup section, select a machine that's comparable. In this case, 3-axis toolpaths are in the setup section, so we'll pick a standard 3-axis machine. Then select the stock tab. Inside the stock definition, enter a stock. Then once completed, hit add, hit OK. To enter SURFCAM machine simulation, it can either be done one of two ways. First, select the button inside the machine simulation on the Operations Manager, or the main core interface button on the main toolbar 1. Upon entering machine simulation, it will read in the current machine definition selected, as well as the job and the stock model as well displayed on the screen. At this point, we'll start a new machine. Moving over to the Machine Definition tab, select the New Machine button. Then select a new name for the machine. In this case, it's a 3-axis machine. We'll say 3-axis. Give it a name, 3-axis Cincinnati. Once the name is selected, we'll begin importing models for this specific machine. But before we do that, let's review the models process with regard to building specific machine components. Machine components are built with standard solid modeling systems of some type. Once these models are built, they are saved as STL models, and then those STL models are read in as machine components. These components are modeled relative to the origin of the machine. Typically, the origin is positioned at the top center location of the work table, as seen here. Also notice, if we read in other design components that we previously designed, we'll append those to the file and display those as well. Again, notice they are built relative to the origin. Here we'll change the color so you can see how these models were designed. Once they're built relative to the solid modeling system, those models are then saved as STL files and read in as components to the machine simulation. Back in machine simulation, we will use those previously built STL solid models as components and import them into machine simulation to build our machine. At this point, we will add any component that is stationary. For example, the floor, the machine body, the machine shroud, or any type of barrier that is non-moving. To do this, we'll right mouse button select in the machine's name, select Add Geometry, then we'll go and select the body of this core machine. Once we imported the body, it's positioned. We can also show the machine body in color. Can change the name of it. We'll call the ID of this machine body. If you read in the wrong machine file, go down to geometry and select the button, and it'll allow you to change out the model that it has as named body. Next thing we'll do is we'll start to begin the layout or design of the axis layout of this specific machine. Since it's a 3-axis machine, we'll need to define the primary axis. In this case, the x-axis would be the primary axis on this machine. To do this, right mouse button select in the name, go to add additional axis, select x-axis. Once you select x-axis, the ID will be displayed for the machine for the x-axis. This can be renamed or changed. We'll have the show slider option, which will display the axis control on the bottom of the screen. It'll also display direction. Direction of this specific axis. Currently the positive direction is the x-axis and it's lined up on the x direction globally. Again, to change this axis positive direction, simply change the sign of that variable, or if the axis is moving in the wrong direction, enter the direction vector that axis is aligned to. Additionally, the axis defines the limits of this specific axis. In this case, the limits of this axis are minus 30 and positive 30. Once you enter in those values for the limits, notice the axis control will display that limit from 30 to minus 30. Now, we add any specific geometry that specifically moves with the x-axis. Right mouse button select, add geometry, go to bed 2 for a subtable. This table is attached to the x-axis. Again, we can rename that subtable. Can give it a different color. Change the name. And to see proper movement, go down to the Axis Control tab. Move the cursor up or down, or drag the slider. Notice it moves properly. Another thing to note, when the table was selected, it came in exactly where it was modeled, making modeling and designing a machine very simple. Right mouse button select on the slider to set it all back to 0, and the table will reset back to 0. Next thing we'll do, we'll add any other subsequent axes relative to this axis of the x. Since the y-axis moves with the x-axis, the y-axis is the child of the x-axis. The x-axis is parent. To determine if an axis is going to be child or parent, a primary or parent axis is the axis that when it moves, other axes move with it. So in this case, when the x-axis moves, it will move the y-axis table. So to add our next axis, we need to add that under the x-axis. To do that, select the x-axis, right mouse button select, add translational axis, select the y-axis, then the y-axis will display an update. Notice it has the ID, the direction, the limits. We can right mouse button select, add geometry to this specific axis. This axis is the main core bed or table. When we import that axis here, we can rename it for the ID. If we want to change the color, we can. In this case, notice that the y-axis limit is between 1,000 and minus 1,000, so we can go back to our y-axis, select the y-axis. From there, change our value, minus 15 to 15. Now notice the axis control updates as well as shows the slider based on the setting here. If we select that axis, wheel it with the wheel of the mouse, notice the y-axis moves. And again, notice if we select the x-axis, notice the y-axis moves with it. Again, being valid since the y-axis is attached to the primary or parent x-axis. Next thing we'll do is we'll add the z-axis. Since the z-axis is an axis that moves by itself, it is not attached to any parent because it is a parent. So in this case, we will add that z-axis to the main core body of the machine. So right mouse button select, 3-axis Cincinnati, select add translational axis, pick your z-axis, and notice now the z-axis is on under its own subheading. Then right mouse button select the z-axis, add geometry, pick the spindle, since we're adding the spindle of this specific machine. Then, if you want to change the color, go change your color. If we wish to change the limit, select the z-axis. Can change the direction if it's wrong, or go down to the z-axis limit. We'll say it's going from minimum 0 to 15. Notice the slider and the axis control updates. If we click on that slider and wheel the mouse, it will show the operation of that specific spindle. If it's wrong, select back on your z-axis, change the direction as needed, or your limits as needed. Next thing that needs to be done is we need to add the dynamic elements. The dynamic elements are the elements that the machine simulation uses to reference specific things. In this case, there's two types of dynamic elements. There's a dynamic element for workpiece or tool set. So in this case, we will select, for the z-axis, we'll select the tool set, since the tool set will be set with regard to the z-axis. Add that. Next thing we'll do is we'll also add the work element, workpiece, work set, which is also attached to the Y table since that's the primary table. So we'll add, select the axis it's supposed to be added to, add dynamic element, click on workpiece set, and now the machine simulation knows where the workpiece is referenced as well as knows where the tool or tool holder are referenced. Next thing to do is add the collision pairs. To add a collision pair, right mouse button select, add collision. We'll add the standard tool and workpiece collision. Check. Then we'll also add a user-defined one. A user-defined collision check will check between other components, say lasers, vices, or a custom check you wish to do. In this case, we'll use a user-defined check. In this case, add object. We'll display all the components for our specific machine. We will select the spindle and the tool, and we wish to collision check it with the workpiece. In this case, it's already added. We can remove it if we wish, or the table. Let's go ahead and remove that workpiece since it's redundant. Once those are added, then we should be able to theoretically check our collision pair. So if we grab the Z slider and move it down to the table, it should indicate a crash. In this case, it does. Once the collision pairs have been added, we can save the machine. File, save as. We'll call it 3-axis Cincinnati. Hit save. Now this specific machine is ready for machine simulation use. If the end user wishes to do a 5-axis or multi-axis machine, the same basic characteristics are used to create those machines. In conclusion, in this video we learned all the basic skills required to build a successful machine models for machine simulation. Users can design and build their own custom machines and use it for SURFCAM's machine simulation.